Right, hi everyone. While we're getting ready, I'm going to say hello. I'm Anthony, actually one of the co-founders of Encode. This is the first event I've run in years, both exercising the muscle and covering for some sickness, and also Flare is a very important partner of ours. Some of you may know Encode runs a validator, one of the leading validators within the Flare ecosystem to help support the network on top of our community and education activities. Nik, you look fantastic.
Well, thank you.
Like putting me to shame. As I was saying, Flare is strategically very important for us, one of our favorite ecosystems, and one we're delighted to support. And this hackathon builds on our education series and will be followed by a wonderful incubator as well. But the important thing is actually not to listen to me. It's to listen to Nik. Nik's going to tell you all about the Flare Data Connector. These events are pretty special. In a world where knowledge is limitless, to hear from experts directly in their voice, in their intended way of delivering things, it is a rare privilege. So I'm sure you'll virtually give Nik a round of applause. But let's look forward to a very good workshop. Nik, thank you so much for joining us, and please do fire away.
Yeah, thank you for hosting us. I think that without further ado, I will just start this workshop now. So yeah, thank you everyone for joining us. This is the third lecture or the third workshop on the Flare Data Connector, proof of reserves for an Omnichain token with Web2 Reserve Reporting. So yeah, this is the last in the series of FDC workshops for this hackathon. In this workshop, we're going to look at proof of reserves. This is an example dApp that we've written that combines the two attestation types that we've seen in the previous two workshops. And it's a pretty little neat thing. So first of all, what is the app that we are making? Or before I go on, if you have any questions, do write them in the chat. I will be keeping an eye out on them, but I'll decide as we go on whether I'll answer them then or at the end, because there will be a 15-minute period for questions at the end of the workshop. So yeah. Anyways, proof of reserves. What this dApp does is, so the problem we are solving is we have a stable coin. This is a coin that is tied up to some other value or a fiat currency. And they claim that such coins can be exchanged one for example, $1. So the stablecoin, the agency that issues stablecoins, they claim certain reserves. They reserves of dollars, and then they issue coins on different chains. What we would like to do is to get the total supply of the stablecoin on each of the chains that the stablecoin is issued on, and compare that to the total supply or total reserves that they claim that they have at their disposal. So perhaps you can already see what the hurdles are that we are here to overcome. So first of all, we need to get the Web2 data about their claimed reserves onto the chain, which is easy. We can do that with the JSON API attestation type. But then there is a second part to it, which is we want to read state data about the stablecoin, the total supply of the stablecoin. And so the question becomes, how can we convert the state data on chain into something that we can actually read, namely an event. And I'll go into that in a little bit. But then the third question is how can we transfer the transaction data onto the chain where we'll collecting everything? There is a question. I'll answer that at the end of the workshop, Peter. So yeah, we have the three problems that we are dealing with. We have the motivation, and now let's look at the code. So I'll be using the code available on the Flare Hackathon starter. This is a starter repository which can serve as a template for your projects. It has use examples for different attestation types. There's also the Flare Developer Hub, and this is a good starting point if you're looking for written tutorials. If you're working with Foundry, this will come in specifically handy because there are Foundry guides written for all the attestation types here. Although the subject of today's workshop is as of yet not covered by the Foundry starter. So with that, let's look at the code. So what I've prepared here is the Flare Hackathon starter. I've cloned the repository and followed the instructions in the README. So yeah, this is the first step. Make sure that you also copy the .env.example file and fill out the relevant fields. So yeah, the first thing that we need to look at is the if we go under contracts, proof of reserves, and token.sol. So first of all, this is the stablecoin, our stablecoin contract that we'll be deploying to Coston and Coston 2 chains. We could go out and find an actual example of a stablecoin, but it's easier if we just take if we deploy our own stablecoin, which allows us to manipulate the total supply values. Flavio will also answer that question at the end of the workshop. So the token contract, it's very simple. Most of the things are just inherited from OpenZeppelin. Yeah, I'll also answer that question at the end, Flavio. So yeah, my stablecoin is just an ERC20 token with some additional values. The starting supply we're setting is just 666 stable coins. It is ownable, burnable, and some additional stuff, but the details aren't that important because the contract we will be defining can work with an arbitrary ERC20 token. Now, the second thing is the token state reader. This is our solution to the second question on of how we can convert the state on a chain to an event. What this contract does is, upon being triggered, it reads the total supply of our chosen token. The address of the token or the token is the input to this function, and it then broadcasts the total supply, the total token supply event with the address of the token and its total supply. I do not have an opinion on stablecoin designs. This is just an example. I'm not getting into that, Yuri. Okay, so the last contract here is proof of reserves. And as you can see, this is the bulkiest contract of the three. First of all, we have a data transport object struct. This one, you can remember a similarly named struct from the first workshop that I held about JSON API. The whole point of this struct is so we can get a solidity encoding to save our JSON API requests to. Then this is the contract itself. The ownable feature is not that important, but first of all, we have two events, good pair and bad pair. This is just so we can debug the contract more easily. And would it be better to emit events like good pair, bad pair on verify reserves too for on-chain observability? Yeah, I mean, they are emitted in that function. It's just that the emission of events is saved to a separate function that is only triggered through the verified reserves. But let's not get ahead of ourselves. The second thing is the mapping from an address to address called token state readers. This is an artifact that I'll be removing in the future. There are two additional values for debugging, debug token reserves and debug claim reserves. This is just so we can see that something is happening when we run the script. What's the advantage of splitting contract logic versus library modules? Could parts of this be moved to a Solidity library? Yeah, I mean, this could be moved to a Solidity library. The thing is that there isn't that many functions here that it would be worth it, because libraries in Solidity just get inlined into the code. So the only advantage would be, I guess, readability. But in this case, it doesn't really matter. I just thought that it would be easier if we split up the whole function into its logical components. Because, for example, I can say read reserves here instead of having a few lines of code there. So, yeah, updated REST, that's also a relic of a previous implementation that should be removed. How do these transaction proofs work? Are they generated by Flare nodes, or do we create them manually for this demo? I'll explain that in a second. I won't be explaining how FTSO works, though. I think that the first workshop was about that. Or maybe if there's enough time, I may explain FTSO, but I'll leave that question at the very last. So, anyways, the main function here is verify reserves. which accepts IJSON proof and and an array of IEVM transaction proof structs as input. As the question asked, and as I've said, I'll be explaining that in a little while. So what this function does is, first of all, it reads the reserves from the JSON proof, and then it reads reserves for each transaction proof in the array, and then sums that up together. And in the end, if the total token reserves are less or equal than the claimed reserves, we return the value true, otherwise we return false. Because in the end, what we want is for the proof of reserves to check that they have sufficient backing for the tokens. It doesn't necessarily need to be exact. So first of all, read reserves on the IJSON API proof. First of all, it verifies the proof. I'll explain in a second how that happens. And then it decodes the proof data to a data transport object and simply accesses its reserves field. Then for the read reserves function on the IEVM transaction proof, that one is a little more involved. And what happens here, please ignore the to-dos because they have been solved already. So the second read reserves function, first of all, verifies the proof, and then it goes through all of the events in the transaction of the transaction proof, and then for each event, it checks that it matches the correct event type, and also that the reader, the contract that emitted the event also matches. This is just a way to filter through all of the events within a specific transaction and find the one that's suitable for us. And when we find such an event, we add it to a total supply. And to be honest, there should only be one such event per transaction anyways, but this is a redundancy built into it. But anyways, if this succeeds, we emit the good pair events just so we can see that something's happening. And otherwise we emit bad pair events so that we can figure out what went wrong. And in the end, we return the total supply that gets summed up. So how do we actually validate the proof? We have what we do in both cases. Please do not get confused by this auxiliary get IJSON API verification function, because we are doing virtually the same thing. The only difference is that the JSON API is still in development, so the official contract doesn't yet have the appropriate function to call, and so we are adding the auxiliary get IJSON API verification function manually. But in both cases, what we're doing is we're looking at a specific, at the contract registry library, which is a library shipped with Flare smart contracts periphery. And this library basically allows us a cleaner way to access the official Flare contracts. Because there is a specific contract on Flare called addressed, I think it's address updater is the name, I think. And the address updater contract basically is a registry storing, mapping contract names to addresses. And this is done for all Flare contracts. And it also has a get contract by name method. So we could use that, but this is very cumbersome and prone to flaws. So in that case, instead we are including a Flare contract, a contract registry library, which just has a handful of auxiliary functions that do just what I described, and so we can avoid the manual call, and yeah, then we just call the verify JSON API or verify EVM transaction methods on the proof, and they will be verified on chain. So yeah, this is the proof of reserves contract. Now, let's. There was a question that I thought I'd answer right now, but it slipped my mind, and I won't go searching for it now. Let's look at the. Let's look at the scripts for proof of reserves now. If we go to scripts, proof of reserves, there are a few files. Let's first of all look at the config file. This will be important in a second. There are three basically identical scripts. So deploy token type script. This one deploys and verifies the token contract on a selected chain. And let's just run that right now. So I'll run the selected text in active terminal. And what we need to do with this is copy the values we get into the config TypeScript file. The second one is deploy token state readers. This one does the same thing, but for the token state reader contract. So here we can see that my stablecoin was deployed to this address on Coston. So let me copy that and move that to the token address for Coston. And there's the one for Coston 2 as well. So let's just do that. Next, let's deploy the token state reader contracts. We will also deploy them on both Coston and Coston 2 chains. And while we wait for that, let's also open the deploy proof of reserves. I'm just going through the busy work here. There will be more Flare specific stuff in a second. So yeah, this is the custom address. Let's put it into the configs under reader address. And we're still waiting for custom 2. Here it is. Cool. Let's also change that. And now let's also deploy the proof of reserves. But we'll also only be deploying this one on custom 2 because we do not need this one. We only need this on one chain, the main chain we're operating on. That's the whole point. We're bringing all of the data onto a single chain. There's a question: what changed with custom 2 versus custom 1? Okay, so real quick, Flare has 2 official mainnets. So the Flare chain and the Songbird chain. The Songbird chain is a canary network for Flare, and then custom 1 and custom 2 are the test chains for each main chain. So custom 1 is the test chain for Songbird, whereas custom 2 is the test chain for the Flare mainnet. Yeah. Anyways, let's also copy this one into the configs under the proof of reserves address. Okay, so we still haven't done anything with Flare, and the next step also won't be anything Flare specific. So the activate token state readers, what this script does is basically gets the stablecoin that we have just deployed. It does so for each of the chains. How does it know which chain it's on? Well, first of all, we specify the network in the command, and then we can access it in the code. And depending on that, we can get the appropriate value out of the mapping. And so we basically just activate both broadcast token supply functions, which emit the event, and that will also give us a transaction hash that we can then update configs with. So, okay, this one is going much faster than the other ones. So, yeah, let's update the configs. And the reason why I'm doing all this manual labor, so to say, is that if you wanted to add an additional chain, I think this clearly demonstrates how what steps all are necessary to do such thing. So if I spell it out, we need to add additional entries to all of the mappings except for proof of reserves address, because that one doesn't change, or it does change, but it's a single value. And there will be a few changes in the last script that we'll look at. But other than that, this script is very easy to expand to additional chains. Though I hope that this example serves more as a proof of concept or an inspiration what can be done with Flare's contracts. So yeah, the last one is the verify proof of reserves script. This one will actually get the data, make the FDC Flare data connector produce fetch the data and produce the appropriate proofs. First of all, let's ignore this line here. First of all, I need to clarify that the code that you see here is a bit different than the one on the starter. I will update it tomorrow, but as it happens, the URL that we were accessing beforehand stopped working just today. So I had to change the things up quite quickly. And what I've landed on is I just deployed a JSON that looks exactly as the one that we would get back from the URL that we were accessing previously. And I deployed that, or I pushed that JSON onto my GitHub. Is verify proof of reserves designed to read this config file dynamically? Yes. It reads the file dynamically, or at least those values. There are a few things hard-coded into this requests object. But other than that, no, it is dynamic. It doesn't dynamically store them, which would be an update. As a side note, this is not a production-ready code. This is an example that's meant to be easily cut apart and used in some other project. Of course, when you are doing this, you'll probably be streamlining the whole process. But I mean, the basics are there if you want to read. I mean, if you want to read some other data, it's clear how you can do it from these things here, from what's written already. Yeah, so anyways, let's quickly look at this address. It's very simple. It returns only a single value field. But the value here matches the one that we were getting back at the format here matches the one that we were getting at the original URL. Oh, before I got sidetracked, what I was trying to say is that what I discovered doing this, or what I realized, is that actually deploying a static JSON onto your GitHub and providing that as URL is actually a very good way to test your code quickly, because you don't have to deal with issues that arise from, I mean, the GitHub already provides all the necessary requirements for a JSON API, the station type, to work. It is a static URL. It returns a JSON, and that's it. So, yeah, actually, this is a very good way to test your projects, and I'll be updating the example to that URL in the future. So anyways, here first of all is the requests object. So as you can see, the requests object matches the three requests we'll be making. The one is to the Web2 API that I've just shown. If you want to know more about accessing Web2 data, look at the first Flare Data Connector workshop. The video is available on Discord and on YouTube, of course. So that is the second lecture. And then there are two requests for getting the transaction data of the two transactions that we've saved into our map here. And if you want to know more about how a EVM transaction attestation type works, look at the third workshop video, because we go over the EVM transaction attestation type there. Yeah, let's quickly look at how FDC, so Flare Data Connector, works. If we go to the Developer Hub and click on FDC, we can then scroll down to Workflow Overview, and the user workflow has a handy graphic here. So, really quickly, we have some data that we want to collect. In this case, it's a Web2. It's the claimed dollar reserves and the state, or rather transactions, on the two chains that the stablecoin was deployed to. So we need to formulate a request for the FDC protocol. And we could formulate the request manually. And if you want to know how to do that, look at the written guides. But the far more easier way is to just contact the verifier server with our request, with the data that we want to request, and it will formulate an ABI encoded request for us, and then we can just send that data to the FDC protocol. So I think the question that I had in mind corresponds to what I'm just about to explain, and that is what happens in the background is that we forward the request to FDC, and the FDC, the Flare Data Connector protocol, which is an enshrined protocol, spreads the request to all the data providers, which are validators of the Flare chain, and they first of all inform us whether they can access the data or not, or they broadcast that information. And if enough of them, more than 50% by the total stake they have, if more than 50% say they can, then the request is approved. And so the data providers are required to go get the data, encode it as a Merkle proof, and then all of them review that proof, and the proof is written on chain. So the data providers are actually storing the data then. And what we do then, once the voting round has finalized, we go to one of the data providers, to their DA layer, and we ask them to give us the data as well as the proof. And so we can then send our data and proof to our smart contract. This would be proof of reserves in our case. And we can contact FDC with the proof that we've been given and the data. We go to FDC and we check if the data and the proof match to the one that has been written on chain. And that way we can know that the data that we received really followed the FDC procedure, that it really is the response to what we have asked. So yeah, I won't go too much into the detail of doing all this because I already explained that in the previous two workshops. but real quickly, we prepare JSON API attestation requests and transaction attestation requests. We do this in the function here. We store the ABI encoded requests in a mapping from chain to the bytes. We then submit the attestation request to the FDC, which will commence the whole process. And then once the rounds have finalized, we also retrieve data improves for the for all 3 requests. And after that, we actually, okay, there's a preparation step involved. But afterwards, we submit our data. So in the prepare data improves step, we pack the data improves into the iJSON API and iEVN transaction .proof structs, and these are the structs that we can then actually insert into our proof of reserves contract. Of course, run on the appropriate address. So I think there was a question whether we have to prepare them manually. Yes and no. I mean, you can just take them out of this example. You have to ensure that the data is formatted correctly as iJSON API proof or EVN transaction proof, because that is the format that is the type of the parameters that are accepted by our contract. But it isn't hard work. It's just placing the correct values into the correct fields. There's no encoding shenanigans that you have to think about. And yeah, that is the whole process. And I'll actually run it right now as I get to answering the questions. The logs are so what am I missing? Let's see. The logs are somewhat lacking as of yet, or rather the logs lead quite a lot to be desired, and I think I'll update them in the future. But anyways, this is the request for the verifier server for JSON API. This is the JQ filter that we are applying to the JSON that we are getting from the URL, from this URL here. And this is the Solidity encoding, the Solidity ABI signature of the struct that we are saving to. If you want to understand this better, go look at the second workshop. Then this is the response we get from the verifier server, the ABI encoded request. Then there's the request for the transaction on Coston and the one on Coston 2, the ones containing the events. And then we come to the actual submit step to FDC, and we need to wait for this around here to finalize. You can click on the link, or yeah, let's just do that. So We can see how the round is progressing if we follow that link. So on Flare Systems Explorers, I don't know which one of these is ours, but since all of this is green, it means that all of the data providers claim that they can prove basically everything that was asked of them in this round, which includes our requests. And if you go to advanced and finalizations, we can see whether the round has been finalized. And I think that, yeah, that was our round. So there are some proof requests to the, so yeah, this is the proof request to the DA layer server. And what we get back from the DA layer server is a response hex that we have to decode to, well, in this case, to iJSON API.response struct. Here are the proofs for our request. This array can also be empty. In that case, the Merkle root itself is the proof, but that happens only when there is a single request that round. This long thing here is for the transactions, and the second transaction is actually longer. And what we get back is that the reserves are sufficient, which is what we would expect. Now let me see if I can get, yeah, I think this is the one. Perfect. Nope, it's not this one. Never mind. Let's scroll down a bit. What I'm trying to show you is that we can open the contracts in the Explorer. So in the Explorer, we can see the transactions that have been made, the verify request. If we go under contract and read write contract, we can find the all debug values. So debug claimed reserves 1 million, which is correct, with the understanding that we just cut off everything that succeeds the decimal point. Then the debug token reserves are just the sum twice the 666. Of course, this value is much larger here than the dollar reserves, but after the conversion, it becomes much smaller. Also, we can look at the transactions, and specifically verify reserves one, and logs. And here we can see which pairs were good pairs and which pairs were bad pairs. Yeah. Okay, this one is a bad pair because the reader contract in this case isn't actually the reader contract. This transaction is something else entirely. But this is all for the proof of reserves. Let me just take a sip of the water and we'll get to the questions in a second. Okay, I'll start. Let's just start at the end for change. So Disney asks, what happens if the verifier server is compromised or sends incorrect data? How is that mitigated? First of all, there is no single verifier server. There are multiple verifier servers. As for verifier server, you can see if the data. Okay, sorry, I don't know if you're asking about the verifier server or the DA layer server or the DA layer provider. I'll answer for both. So all that verifier server does is prepares the ABI encoding of the request for you. So that's the the bytes here. If it does something incorrect, FDC just won't be able to provide a request, and once you decode the data, you will be able to see that the request was faulty. Because if you look at this response hex, you can decode that back to event transaction dot response struct, and you'll see that the values in that are incorrect. So that would be how you can see that the verifier server was compromised. And you can always construct the request by hand. But I don't think that the point of an attack, the verifier server would be the point at which an attack would happen, because it's just a tool. Now, as for the DA layer providers, they could actually send incorrect data, but there is, I don't remember where exactly, but you can track the performance of the DA layer providers, how good they got the requests, if they were faulty or not. And there's multiple of them. And if you see that one of them falls behind in its performance, you can just switch to another one. And yeah, that's how it's basic. If enough of them were compromised, that more than half of the stake would vote for would provide proofs for incorrect information. At that point, the whole chain has been compromised. So the second question, also out of interest, what would need to change to port this architecture to another chain, e.g. Ethereum, Celeste, etc.? That's a very good question, actually. And it's something that I wanted to mention. So first of all, if we wanted to add another source, we would do so here. So it would, we would just add another field. Now, if we wanted the whole, if we wanted to translate the whole FDC functionality onto another chain, there's a special contract among the Flare official contracts called Relay. And if we just move that Relay contract onto Ethereum, for example, we could port all of the transactions onto Ethereum, and we would basically get the whole of Flare on Ethereum, or the whole functionality of Flare. And as a matter of fact, we already have a script that's capable of relaying the whole Relay contract onto another chain. And I think that we'll be working on that in the future to make that even more streamlined. Okay, I'll scroll to the top now and go from there. So what use cases would you like to see that use the data connector? Any tips for the hackathon? I mean, if you just find some interesting new data that you can collect, that's a lot already. If you can manage to do something with DeFi, I think that's something that's very desirable at the moment. So yeah, like even I think that one of the side tracks is an innovative data source. So if you find something very interesting, that actually might qualify you for a side track, if nothing else. I hope this answers the question. Is there a Flare specific GPT or MCP? No, I don't think so. What mechanisms does the FDC employ to ensure the security and reliability of data imported from external sources? I think I've just explained that. So the JSON API, this is perhaps another thing that I could mention. The JSON API is the most risky of all, because you have to trust the data source. But for EVM transaction, for example, you can set up your own RPC, and in that for the chain that you're interested in, and in that case, you don't have to trust anyone. Cool. And also, where can I get a bow tie like that? Yeah, I don't think you can, because I saw this one myself. But otherwise, you can try looking for it online, I guess. Although I think Europe is kind of bad with the bow ties available. Anyways, what do you think is the best stablecoin design? Oh yeah, I've already answered that. That one as well. So how do these transaction proofs work? I've explained that already. They're generated by the validators or data providers, as they're called on Flare. The question about FTSO, I'll leave for the end. What kind of attack vectors could exist if the proof verification logic is flawed? I don't really know how to answer that question. I don't think the logic is flawed, so but I'm not into the security. I'm not part of the security department, so I don't have a very good answer to that. Okay. Let's just. I think this is all. The FTSO question, I don't think we have time for that, do we, Anthony?
We are, unfortunately, at pretty much the final 30 seconds. Yeah. There's always Discord, and there's always Discord of Encode, Discord of Flare, to continue the discussion. Nik, is there anything else you want to add, flag, or say?
Just go to the developer hub. There's plenty of guides there as well as the explanation on how FTSO works. So, go there. Otherwise, I wish you good luck and good hacking.
And I second those good wishes. Nik, thank you so much for a very erudite and cogent look at the Flare data connector and all things inspirational for the hackathon. We hope to see some very good things building not just on things learnt in these workshops, but the education series as well. You will hear from us. I'm sure you'll keep hearing from us on all things Flare Hackathon as we approach submission dates and get to see all the brilliant things you guys build. In the meantime, Nik, we're very, very grateful to you. Thank you so much to you and your bow tie. This video will be available publicly to all hackers to go over again and use for future building throughout this event. Otherwise, guys, thank you very much. Have a wonderful evening, morning, afternoon, wherever you are, and see you very soon. Bye, guys.
Goodbye.